Moving on to some AP style questions here. So to start off, we have a ball attached to a string going around in a horizontal circle. And we want to know what would happen if we change the radius of the circle to 4 times as much, assuming the same force is applied. So this is one where we're going to set up our original situation and also our new situation. So in this case, we're thinking about the centripetal force being applied by the string, or our tension force. And we know that that stays the same. So I'm going to imagine this situation here where the ball's going around in a horizontal circle, and we have that inward force of tension, which ultimately leads to our inward acceleration. Now there's probably some vertical forces here as well, but I'm not really concerned with those in this situation. Based off of this, I'm going to set up my F equals ma, and the reason I'm doing that is I do know that this force stays the same, and so I need to get that centripetal force, which is tension in this case, into my equation here. So my original equation is going to be Ft equals m times my acceleration, which is v squared over r. Okay, that force of tension is the only force keeping it moving in a circle. My new equation, Ft, stays the same. The mass of the object stays the same. My velocity changes, so I'm going to call this v prime squared, and my radius is now 4r. Simple way to combine these, I see that they're both equal to Ft, so I'm just going to go ahead and set them equal to each other. So I have m times v squared over r, we'll change it to a capital R because it does say that was my initial radius, equals m times v prime squared over 4r. I know that I can divide out those m's and I can divide out those r's, and so what I'm left with is v squared equals v prime squared over 4. I'm going to multiply both sides by 4, so I get 4v squared equals v prime squared. I can take the square root of both sides, and I find that my new velocity is 2 times my original. When I take that square root of 4v squared, I take the square root of both the 4 and the v squared. So I have an answer here of d, twice the original speed. Moving on to question 10, we have a situation where we have a coin on top of a turntable, on top of a record, rotating around. And we want to know which of the following directions best represents the direction of the frictional force on the coin when it is in the position shown. So we should know right off the bat that while it's going around in a circle, it has an inward acceleration, so at that point it is accelerating downward. If we think about this coin as it travels in a circle, there's really only one force that can exist to cause that inward acceleration. Okay, we need some force inward to create this acceleration. The only force that we really have that could do that is friction. And so that force of friction is that inward force. So when we're at that top point, that force of friction is just down, making the answer C. So we're going to start here with an AP style question about a satellite orbiting a planet. All right, we know it's orbiting at some height above the surface. Okay, so it's going to look something like this. Here's our planet. There's our satellite orbiting at some height above the surface, 5 times 10 to the 7th meters. And so we know that distance. And so what we want to do here is we want to think about what else we need to know in order to figure out the orbital velocity of this satellite. So 2 ways of thinking about this. The first is we could think about Kepler's third law, and we could try and find the period of orbit first, and then use that to ultimately get the velocity. So if we're thinking about Kepler's third law, we're going to need m, which is the mass of the planet. Okay, and we also need the orbital radius. Now to get that orbital radius, that's going to be this height above the planet, but we also need to know the radius of the planet itself. Those two together are ultimately going to give us big R, that orbital radius. So we need to also know the radius of the planet. And once we have that information, we could solve for the period. And once we know the period, we could then do v equals 2 pi r over t in order to get the orbital velocity. The t we would have found up here in the first part, and the r is going to be the same r that we used here, that orbital radius, which consists of the radius of the planet plus the height above the surface. So that's one way we could think about it. The other thing we could think about is we could think about circular motion, okay, and F equals ma. In this case, we have the force of gravity is the force that keeps the satellite in motion, and its acceleration is a centripetal acceleration, so we can sub in v squared over r. Now we know that the force of gravity is g m1 m2 over r squared, and that's going to be equal to m times v squared over r. And what we're going to see is that the m, one of the m's, in this case the mass of the satellite, cancels out, and what we're left with is that m, which is the mass of the planet, and this r here, which once again is the height above the surface plus the radius of the planet. So whichever way you think about it, what it ends up leading to is that you need to know both the mass of the planet and the radius of the planet. And this was one where we select two answers, so we should have two possibilities here, or two ones that we need in order to solve for it. Moving on to this next multiple choice question here, if spacecraft X has twice the mass of spacecraft Y, then true statements about X and Y include which of the following. So let's go through these one at a time. On Earth, X experiences twice the gravitational force that Y experiences. That's absolutely true. We can think about that going all the way back to Fg equals mg. The force of gravity is just going to be the mass times the acceleration due to gravity. So if it's twice the mass, twice the acceleration due to gravity. On the moon, X has twice the weight of Y. Keep in mind that weight is the same thing as the force of gravity. So this one is also true. Their weights would be different on the moon, okay, because the acceleration due to gravity is less on the moon. However, that ratio of X having twice as much would still be the same because X will still have twice as much mass even on the moon. So statement 2 is true. And lastly, when both are in the same circular orbit, X has twice the centripetal acceleration of Y. So there's really two pieces to this one. The first is that centripetal acceleration is v squared over r. So we don't see mass in there at all. The only thing that affect the centripetal acceleration are the velocity and the radius. Okay? Now, they're going to have the same radius if they're in the same circular orbit, but will they have the same velocity? And the answer here is yes. We know from Kepler's third law that the period and therefore the velocity depends only on the distance. Okay? So if they have the same radius, they're going to have the same period of orbit and therefore the same velocity, and that means that this one is not true. Their centripetal accelerations will be the same. X will not have twice the centripetal acceleration of Y. So that leads to the answer that only 1 and 2 are true, so that is choice C. So we have another experimental design one shown. So we have this device that's shown in the picture here where there is a string going through a glass tube and it's attached to a ball that goes around in a circle on the end here. We have a spring scale attached to the cord. Okay, and we're swinging the ball around with a known radius of r. And so what we want to do is we want to derive a procedure that would allow us to determine the mass of the ball based off of this setup. So what I'm going to do is I'm going to skip right here to part 4 of this. I'm actually going to answer that part first because that's the how would you actually get this part, and I think that's going to make it easier to answer parts 1 through 3. So to start thinking about 4 here, I'm going to think about the forces acting on the object. I'm going to go ahead and draw those forces. So the force we're going to have, we have the force of tension acting on the ball, of course. That's the force keeping it moving in a circle. This is once again the side view here. I'm also going to have a force of gravity going down. So that's all the forces I really have for now. Now there is this line here about assume the string is horizontal. We'll come back to this idea because you're probably thinking, well, why isn't this object accelerating down? That is something we'll address in a second. But for now, we really actually only care about this force of tension anyway because that's the force keeping it moving in a circle. So we can go ahead and set up our F equals ma. So our force is in the x equal max. The only force we have causing that inward acceleration is that force of tension. So that's equal to the mass times v squared over r. So ultimately we're looking for the mass here, so I'm going to go ahead and rearrange this equation to solve for that. So I'm going to multiply both sides by my radius r and divide by v squared, and so my mass is going to be ft times r over v squared. Now let's think about the things that we know. We're told that the radius is known here, so we don't have to worry about finding that. And the tension we can get from the spring scale, okay, so we don't have to worry about that part either. However, we do need to figure out how we're going to determine this velocity. So we know we have a stopwatch, and we do have a way of finding the velocity of an object moving in a circle, and that is 2 pi r over t. Once again, we know the radius here, so we can time the period, okay? And we can substitute that in. So we should write a few words here to supplement this procedure. So the first thing I would say we're going to do is we're going to use our measured period, use this time that we're going to measure with our stopwatch to solve for our velocity. And I'll go ahead and cite that equation. Then we're going to take that over here and use this equation to ultimately solve for mass. There we have it. And the one thing we maybe add in parentheses is just acknowledging that radius is known. We were told that, so that's not something we need to calculate, but it's probably a good idea to mention that. So there's part 4. There's what we ultimately need to do. So we see the two things we need to get data on are the force of tension and the period. So that's going to help us go ahead and do parts 1 through 3. So let's go ahead and do that now. Now that we have that, what quantities would be measured? It would be the force of tension in the string and also the time for one revolution, or the period. Next asks us what equipment we would use and how that equipment would be used. For this one, it's not that difficult because we're told exactly what equipment we have, but we should still mention what that equipment is and include this brief label diagram of the setup. So there we have it, a statement of the two pieces of equipment, the spring scale for tension and the stopwatch for the period. And then I'm going to include a brief diagram here. We kind of have one given, but we should include one anyway. So there we have a very basic diagram showing the mass attached to the string with the spring scale attached to that, and then the stopwatch on the side. And so that's really all we need for that. For the last part, describe this experimental procedure. First of all, we always want to state what we would actually do to complete a trial. So we're going to swing the ball in a circle at a constant speed. Next, I would say we're going to measure the time for one period and record the force while we're spinning it at this constant speed. The last thing I would say, and this really relates to this line here, explain how to reduce experimental error, is that we would repeat this several times, and ideally we would swing it at various constant speeds. Each time we are going to swing it at a constant speed, but changing that constant speed is only going to help our readings and shouldn't affect the mass of the object, obviously. So there's part A. I'm going to go ahead and erase this and move on to part B. So for part B, the first thing we're actually asked to do is draw the forces acting on the ball. So I'm going to take my free body diagram that I had drawn earlier and use that there. So that's what the forces acting on the ball would look like. We already had done that. And now we want to explain why it's not possible for the string to be perfectly horizontal. And that's where we come back to this idea that we have gravity acting down on this object, but as you can see, nothing to balance the force of gravity. So the reason why it can't possibly be completely horizontal is we need some force going up to balance the force of gravity. And where do we get that force from? Well, if our tension is up at an angle, then we're going to have components of tension, and that vertical component of tension can balance the force of gravity. So to explain this, I'm going to start by just stating that the force of gravity is acting down on the object. And then I'm going to say that there must be a force to balance that downward force of gravity, since the object is not accelerating vertically. And then the last thing to kind of really tie this all together is if the string is at an angle, the y component of tension can provide that force. But if it's completely horizontal, there is no y component of tension. And I'm just going to wrap it up by saying, therefore, the string must be angled, bringing all of this together to really get back at the ultimate question of why the string cannot be perfectly horizontal. All right, moving on to this AP problem, which actually was from the 2018 test. So this is an actual AP problem here. We have the spacecraft here that is orbiting the Earth at some distance r from the center of the Earth. Okay, it's a clockwise circular orbit as shown. The first thing we want to do is just draw and label the forces acting on the spacecraft. And so we know that when something's in orbit, the only force acting on it is Fg. Okay, and so it's going to look something like that. For part B here, we want to derive an equation for the orbital period of the spacecraft in terms of m, the mass of Earth, and r, the radius, and also physical constants as appropriate. So I'm going to start here with F equals ma. Basically, they want us to derive Kepler's third law. We know that this object is moving in circles, and gravity is the only force acting on it, so we can say Fg is equal to m times v squared over r. Since we're dealing with the force of gravity between a spacecraft and the Earth, I'm going to use the universal law of gravitation, okay? And then I'm going to start plugging in some of the things we know here. So we know the one mass is the mass of the spacecraft, which is just m. The other mass is the mass of the Earth, which is this capital M-E. The radius of the orbit, which is how far away the spacecraft will be from the center of Earth, is capital R, and that's equal to m over here times v squared over capital R once again, all right, because that distance is the radius of the circular path taken. So a few things will divide out here, okay, and what I'm left with is this expression, gme over r is equal to v squared. Now, since we ultimately want the period, I'm going to make use of the equation for an object traveling in a circle, 2 pi r, and I'll use capital R because that's the radius of the orbit over t, and I'm going to substitute that into this equation that I have down here, and what I'm going to be left with is gme over capital R is equal to 2 pi r over capital T, that entire quantity squared. We go through and square everything in that equation, and we end up getting 4 pi squared r cubed over t squared. I'm going to go ahead and cross multiply here, and I end up getting that t squared times g me, the mass of the Earth, is equal to 4 pi squared r cubed. And so for a final answer, I can say t squared equals 4 pi squared r cubed all over gme. I, of course, could take the square root of that, but given that this is Kepler's third law, it's okay to just leave it in that form. Moving on to the second part of B, it asks about a second spacecraft with a mass of 2m being placed in the same orbit. And we want to know if the orbital period is greater than, less than, or equal to, and our answer to is equal to. And the reason is, two reasons really. Number one, we see right here in this step that the mass canceled out, so the mass of the spacecraft actually doesn't matter. If we want to go a little bit more conceptual, we can say that, even though it would have a bigger mass and more force would be required to keep it moving in a circle, there also is a greater gravitational force acting on it because it has more mass, and those two effects cancel out. All right, and part C here asks if the spacecraft is moved to a new orbit that has a radius greater than r, as shown here. So there's our new orbit. Would the speed of the spacecraft in this new orbit be greater than, less than, or equal to the original speed? And the answer here is less than. And the key really is this step in our derivation, which shows us that v squared is proportional to 1 over the radius of the orbit, okay? And so as we increase our radius, that's actually going to decrease the velocity of the spacecraft moving in that orbit. The further and further away we get from the planet, the slower and slower a satellite or spacecraft orbiting will travel to maintain an orbit at that distance.